CO2 corrosion damage mechanisms as a part of uniform or localized loss of thickness. Description of CO2 corrosion based on API 571, carbon dioxide or CO2 corrosion results when CO2 dissolves in water to form carbonic acid or H2CO3. The acid may lower the pH and sufficient quantities may promote general corrosion and/or pitting corrosion of carbon steel. CO2 corrosion damage, description and characteristics. CO2 corrosion, also known as carbonic acid corrosion, occurs primarily in water systems where carbon dioxide or CO2 is present. CO2 can dissolve in water to form carbonic acid or H2CO3, which can lead to the corrosion of metals, especially carbon steel and low-alloy steels. This type of corrosion is particularly common in oil and gas industries, water treatment plants, and in boiler systems. Number 1 is corrosion process. Dissolution of CO2. When CO2 comes into contact with water, it dissolves and forms carbonic acid. The reaction can be represented as CO2H2O equals H2CO3. Number B, acidic environment. Carbonic acid dissociates into bicarbonate or HCO3, and hydrogen ions or H, leading to a decrease in pH and an increase in acidity of the water. The presence of H ions contributes to the corrosive environment. Number C, metal reaction. Metals in contact with this acidic solution undergo oxidation. The corrosion process can be described by the following general reaction for iron or Fe, Fe2H equals Fe squared 2H2. Here, iron is oxidized to ferrous ions or Fe superscript 2, contributing to metal loss. Number 2 is characteristics of CO2 corrosion. Number A, of characteristics of CO2 corrosion is localized corrosion. CO2 corrosion often leads to localized corrosion phenomena, such as pitting and crevice corrosion. This is particularly pronounced in areas where CO2 can accumulate or where stagnant conditions exist. Number B, of characteristics of CO2 corrosion is rate of corrosion. The rate of CO2 corrosion can be influenced by several factors. CO2 concentration. Higher concentrations increase corrosion potential. Temperature. Elevated temperatures can accelerate reactions, leading to increased corrosion rates. pH levels. Lower pH, or higher acidity, due to carbonic acid enhances corrosive effects on metals. Presence of other ions, sulfates, chlorides, and other ions can either exacerbate or mitigate corrosion depending on their nature and concentration. Number C, of characteristics of CO2 corrosion is surface appearance. The metal surfaces affected by CO2 corrosion often exhibit a rough texture, with potential pitting marks. Rust formation can present as reddish-brown discoloration on the surface. Number 3 is implications and consequences. Number A, of implications and consequences is material degradation. CO2 corrosion can result in significant material loss and reduce structural integrity of piping systems, pressure vessels, and equipment. Number B, of implications and consequences is increased maintenance costs. The need for regular inspections, repairs, or replacements can lead to increased operational and maintenance costs. Number C, of implications and consequences is operational failures. If left unchecked, CO2 corrosion can result in leaks or catastrophic failures, leading to safety hazards, environmental concerns, and unplanned downtimes. In summary, CO2 corrosion is a significant concern in various industrial and utility applications where carbon dioxide is present in aqueous environments. Understanding its mechanisms, characteristics, and preventive measures is crucial for managing and mitigating its impact on equipment and systems. CO2 corrosion affected materials based on API 571, carbon steel and low-alloy steels. CO2 corrosion damage predominantly affects a variety of materials, especially metals, used in pipelines, vessels, and equipment in industries such as oil and gas, water treatment, and power generation. The degree of susceptibility to CO2 corrosion can vary based on the material's composition, treatment, and environmental conditions. Here are the primary materials affected by CO2 corrosion. Number 1 is carbon steels. Carbon steels characteristics. Carbon steels are widely used due to their cost-effectiveness and mechanical properties. However, they are particularly susceptible to CO2 corrosion. Carbon steel's mechanisms. CO2 reacts with the moisture, forming carbonic acid, which leads to corrosion in the presence of carbon steel. Carbon steel's symptoms of damage: pitting, localized corrosion, and general thinning of the metal. Number 2 is low-alloy steels. Low-alloy steels characteristics. These steels contain alloying elements that enhance strength, toughness, and corrosion resistance compared to regular carbon steels. Low-alloy steels resistance. While low-alloy steels offer better performance than standard carbon steels, they are still vulnerable to CO2 corrosion in acidic environments, especially if protective coatings are damaged. Number 3 is stainless steels. Stainless steels characteristics. Stainless steels contain chromium and other alloying elements that provide resistance to general corrosion. Stainless steel's resistance. While they exhibit significantly better resistance to CO2 corrosion than carbon steels, certain stainless steel grades, particularly those with lower chromium content, can still suffer localized corrosion such as pitting and crevice corrosion in carbonic acid-containing environments. Stainless steel's grades affected: ferritic stainless steels, like 430, and some austenitic grades, like 304, can be more susceptible than higher alloyed grades, like 316 or duplex stainless steels. Number 4 is copper and copper alloys. Copper and copper alloys characteristics. Copper and its alloys, such as brass and bronze, are generally resistant to many types of corrosion but can still experience CO2-related corrosion, especially in low pH environments. Copper and copper alloys symptoms of damage. Corrosion can manifest as desinsification in brass alloys and localized pitting. Number 5 is aluminum and aluminum alloys. Aluminum and aluminum alloys characteristics. Aluminum has excellent corrosion resistance due to the formation of a protective oxide layer. Aluminum and aluminum alloys resistance. However, in acidic conditions generated by CO2 corrosion, aluminum can experience localized attack, leading to pitting and loss of material. Number 6 is cast iron. Cast iron characteristics. Cast iron is sometimes used in piping systems but can be susceptible to CO2 corrosion, particularly in the presence of moisture and acidic conditions. Cast iron symptoms of damage. Corrosion may occur as rusting and substrate degradation. Number 7 is coated materials. Coated materials characteristics. Various coatings, such as paint, epoxy, or other protective layers, are often applied to metals to provide corrosion resistance. Coated materials impact of CO2. CO2 corrosion can cause localized corrosion under coatings, known as blistering or delamination, leading to loss of protection and subsequent damage to the substrate. Number 8 is concrete and masonry. Concrete and masonry characteristics. While not metals, concrete and masonry used in infrastructure can be affected by CO2 corrosion, primarily through carbonation processes that lead to the deterioration of embedded reinforcing steel, rebar. Concrete and masonry mechanism. The reaction of CO2 with calcium hydroxide in concrete can lower pH, leading to corrosion of the rebar and reduce structural integrity. In summary, CO2 corrosion primarily affects various steel grades, alloys, and some nonmetallic materials, necessitating the careful selection of materials and appropriate protective measures in environments where CO2 is present. CO2 corrosion critical factors based on API 571, the partial pressure of CO2, pH and temperature are critical factors. Number B, increasing partial pressures of CO2 result in lower pH condensate and higher rates of corrosion. Number C, corrosion occurs in the liquid phase, often at locations where CO2 condenses from the vapor phase. Number D, increasing temperatures increase corrosion rate up to the point where CO2 is vaporized. Number E, increasing the level of chromium in steels offers no major improvement in resistance until a minimum of 12% is reached. CO2 corrosion, also known as carbonic acid corrosion, primarily occurs in carbon steel and is a significant concern in the oil and gas industry, as well as in other sectors dealing with water pipelines and storage systems. The critical factors influencing CO2 corrosion damage include: Number 1 is pH levels. The pH of the environment significantly affects CO2 corrosion. Lower pH levels, more acidic conditions, increase the corrosion rate because carbon dioxide reacts with water to form carbonic acid, which is corrosive to steel. Number 2 is temperature. Higher temperatures generally increase the rate of corrosion. Elevated temperatures can enhance the rate of chemical reactions and accelerate the diffusion of corrosion products. Number 3 is CO2 partial pressure. The concentration of CO2 in the environment impacts corrosion rates. Higher partial pressures increase the availability of CO2, leading to greater carbonic acid formation. Number 4 is presence of water. Water is essential for CO2 corrosion to occur. The presence of a moisture layer promotes the formation of an electrolyte, which facilitates the electrochemical reactions involved in corrosion. Number 5 is velocity of fluid. The flow rate of the fluid can influence corrosion rates. Higher flow velocities can lead to increased mass transfer of CO2 and electrolyte to the metal surface, potentially increasing the rate of corrosion. Additionally, turbulence can prevent the accumulation of corrosion products on the surface. Number 6 is oxygen concentration. The presence of dissolved oxygen can exacerbate corrosion rates. Oxygen can drive the anodic reactions of corrosion, leading to accelerated metal deterioration. Number 7 is material properties. The composition and microstructure of the material can affect its susceptibility to CO2 corrosion. For example, the presence of alloying elements, such as chromium or molybdenum, can enhance corrosion resistance. Number 8 is microbial activity. Bacteria, particularly sulfate-reducing bacteria, SRB, can influence corrosion processes. These microorganisms can produce acids and other metabolites that increase susceptibility to corrosion. Number 9 is protective coatings and corrosion inhibitors. The use of protective coatings or the application of corrosion inhibitors can significantly reduce the rate of CO2 corrosion by creating a barrier between the metal surface and the corrosive environment. Number 10 is electrochemical factors. The presence of electrochemical cells, anodes and cathodes, can influence corrosion rates. The arrangement of these cells depends on environmental conditions, leading to localized corrosion and pitting in certain areas. Number 11 is sediment and scale formation. The accumulation of sediments or scale can lead to localized corrosion, especially if the deposits create differential aeration cells or trap moisture. Understanding these factors is crucial for predicting, preventing, and managing CO2 corrosion in various contexts. Effective corrosion management strategies typically involve monitoring these factors and implementing appropriate mitigation techniques. CO2 corrosion affected units or equipment based on API 571, boiler feedwater and condensate systems in all units are affected. Number B, effluent gas streams of the shift converters in hydrogen plants can be affected. Corrosion usually occurs when the effluent stream drops below the dew point, approximately 300 degrees Fahrenheit, or 149 degrees Celsius. Corrosion rates as high as 1000 mpy have been observed. Number C, overhead systems of regenerators in CO2 removal plants are affected. CO2 corrosion can impact various units and equipment across several industries, particularly in oil and gas, chemical processing, water treatment, and power generation. Here's a detailed list of the key units and equipment that are susceptible to CO2 corrosion. Number 1 is pipelines. Transport pipelines, used for transporting oil, gas, and water. Corrosion can occur, especially where water accumulates. Distribution pipelines, these may experience CO2 corrosion, particularly in environments with wet gas. Number 2 is storage tanks. Above-ground storage tanks, ASTs, especially at the water interface, where corrosive conditions can develop due to moisture. Underground storage tanks, USTs. Similar concerns apply as in above-ground tanks. Number 3 is drilling equipment. Casing and tubing. These components used in oil and gas wells are susceptible to corrosion in CO2-laden environments. Drill strings. Equipment used for drilling can experience corrosion due to exposure to CO2-rich fluids. Number 4 is compressors. Gas compressors. Internal components can deteriorate due to the presence of CO2, especially when combined with other corrosive agents. Number 5 is separators. Oil-water separators, used to separate hydrocarbons from water, these can experience corrosion in stagnant areas. Number 6 is heat exchangers. Shell and tube heat exchangers. Conditions at fluid interfaces can create corrosive environments due to CO2 presence, especially if condensation occurs. Number 7 is valves and fittings. Gate valves, ball valves, flanges, and other fittings, prone to localized corrosion, especially in stagnant areas of piping systems. Number 8 is wellheads and Christmas trees. Equipment managing oil and gas extraction can face significant corrosion risks from CO2 exposure. Number 9 is water treatment systems. Clarifiers, filters, and disinfection systems. Equipment used in water treatment can corrode due to acidic conditions from dissolved CO2. Number 10 is heat recovery steam generators, or HRSG. Used in power plants, HRSGs can experience corrosion where CO2 and water are present, particularly in flue gas condensate. Number 11 is production equipment. Pumps, storage vessels, and other equipment. Various production-related gadgets can be affected by CO2 corrosion. Number 12 is cooling towers. Systems where water can become acidic due to dissolved CO2 are at risk for corrosion. Number 13 is turbines. Certain types of turbines, particularly in geothermal and gas processing applications, may face corrosion in areas where CO2 is present. Number 14 is instrumentation and control systems. Some sensors and control systems in CO2-rich environments can also be susceptible to corrosion. Mitigating CO2 corrosion effectively requires proper material selection, corrosion monitoring, protective coatings, the use of corrosion inhibitors, and regular maintenance practices. Understanding the specific risks associated with each unit and implementing preventive measures is essential for maintaining operational integrity and preventing equipment failure. CO2 corrosion appearance or morphology of damage based on API 571, Number A, localized thinning and/or pitting corrosion of carbon steel. See Figure 485 CO2 corrosion of a carbon steel oil and gas production flow line. See Figure 486, higher magnification view of the corrosion pits in Figure 485. See Figure 487, CO2 corrosion of CS pipe nipple in CO2 contaminated water. Number B, carbon steel may suffer deep pitting and grooving in areas of turbulence. See Figure 488. A view inside the nipple in Figure 487 showing mesa-type corrosion typical of CO2 corrosion. Number C, corrosion generally occurs in areas of turbulence and impingement and sometimes at the root of piping welds. The appearance and morphology of CO2 corrosion damage can vary depending on several factors, including the presence of water, temperature, pressure, carbon dioxide concentration, and material composition. Here are common characteristics observed in CO2 corrosion. Characteristics number 1 is general appearance. Pitting corrosion. CO2 corrosion often leads to localized pitting. These pits may be small but can penetrate deeply into the material, causing significant structural weakness. Uniform corrosion. In some cases, a more uniform thinning of material can occur, particularly in the presence of water and stagnant conditions. This leads to an even decrease in thickness rather than localized damage. Characteristic number 2 is surface morphology. Rough surface texture. The affected areas may exhibit a rough texture, indicating the loss of material and the presence of corrosion products. This roughness can form due to the breakdown of the metal surface as it reacts with CO2 and moisture. Reddish or brownish staining. Depending on the steel alloy and protective coatings, corrosion products may appear as rust, iron oxide, or other reddish or brownish stains on the surface. White rust, in certain conditions, particularly with zinc-coated or galvanized surfaces, a white, fluffy corrosion product may develop, zinc carbonate, due to the reaction with CO2. Characteristics number 3 is corrosion products. Presence of carbonates. The corrosion process can lead to the formation of various carbonate minerals, such as iron carbonate, as CO2 reacts with metals. Oxides. Formation of oxides, like magnetite, may occur in addition to carbonates, contributing to the appearance of the corrosion damage. Characteristics number 4 is leaching and staining. Leaching. If the material is exposed to acidic conditions, leaching may occur, resulting in a softer surface that can further enhance erosion. Staining. Adjacent areas to the corrosion sites may show staining from leachates or corrosion products, impacting the visual appearance of the equipment. Characteristics number 5 is cracking. Stress corrosion cracking. In some environments, especially when combined with other corrosive elements or under stress, CO2 corrosion can lead to cracking, which may follow the grain structure of the metal. Characteristics number 6 is corrosion rate. The rate of corrosion can vary significantly, leading to differences in the appearance based on environmental conditions. In low pH or high CO2 concentrations, pits can develop rapidly. Characteristics number 7 is impact of temperature and pressure. Higher temperatures and pressures can exacerbate CO2 corrosion, leading to more severe pitting and faster material degradation. In conclusion, the morphology of CO2 corrosion damage is distinct and should be monitored closely in susceptible equipment. Regular inspections and appropriate preventive measures, such as corrosion inhibitors and protective coatings, are essential to managing the risks associated with CO2 corrosion and maintaining the integrity of affected equipment. CO2 corrosion prevention and mitigation based on API 571, Number A. Corrosion inhibitors can reduce corrosion in steam condensate systems. Vapor phase inhibitors may be required to protect against condensing vapors. Number B. Increasing condensate pH above 6 can reduce corrosion in steam condensate systems. Number C. The 300 series SS are highly resistant to corrosion in most applications. Selective upgrading to stainless steels is usually required in operating units designed to produce and/or remove CO2, such as hydrogen plants and CO2 removal units. Number D. Steam condensate systems that experience CO2 corrosion are usually the result of operating problems. Number E. 400 series SS and duplex SS are also resistant. Preventing and mitigating CO2 corrosion is crucial, particularly in industries such as oil and gas, chemical processing, and water treatment, where CO2 can lead to significant material degradation. Here are several effective strategies to prevent or mitigate CO2 corrosion damage. Number 1 is material selection. Corrosion-resistant alloys. Use materials that are less susceptible to CO corrosion, such as stainless steels, duplex stainless steels, or other alloys designed to withstand corrosive environments. Coated materials. Apply protective coatings, such as epoxy, polyurethane, to metal surfaces to serve as a barrier against CO2 and moisture. Number 2 is control of environmental conditions. Manage pH levels. Keep the pH level above critical thresholds, typically above 6.5 to 7, to minimize acid formation from dissolved CO2. Remove water. Implement drainage and drying techniques in systems to prevent water accumulation, reducing the risk of corrosion. Reduce CO2 concentration. Where feasible, lessen the concentration of CO2 in the process, which can help mitigate corrosion rates. Number 3 is corrosion inhibitors. Chemical inhibitors. Introduce corrosion inhibitors specifically formulated to combat CO2 corrosion. These may include amines, phosphates, or other chemicals that form protective films on the metal surface. Filming inhibitors. Some inhibitors work by creating a protective film that reduces the metal's exposure to corrosive species. Number 4 is cathodic protection. Impressed current cathodic protection, ICCP use an impressed current or sacrificial anodes to provide cathodic protection to pipelines and storage tanks, reducing the corrosion potential. Sacrificial anodes attach anode materials, such as zinc or magnesium, to structures to preferentially corrode instead of the protected metal. Number 5 is design modifications. Avoid stagnant areas. Design systems to prevent stagnant areas where moisture and CO2 can accumulate, thus minimizing localized corrosion. Proper drainage. Ensure effective drainage systems in tanks, vessels, and pipelines to reduce water retention. Number 6 is routine monitoring and inspection. Regular inspections. Conduct regular visual inspections and utilize non-destructive testing, or NDT, techniques to assess corrosion levels. Corrosion monitoring. Implement corrosion monitoring systems, including probes, coupon tests, and online monitoring techniques, to gather real-time data on corrosion rates. Number 7 is maintenance practices. Cleaning. Ensure regular cleaning and maintenance of equipment to remove corrosion products and deposits that may hold moisture. Prompt repairs. Address any signs of corrosion early with repairs or replacements to prevent further damage. Number 8 is operational practices. Maintenance of operating conditions. Maintain consistent operational conditions that minimize the risk of corrosion, such as controlling temperature and pressure. Chemical treatments. In water treatment systems, consider using chemicals, such as softeners or scale inhibitors, to manage corrosion. In conclusion, implementing a combination of these strategies tailored to specific environmental conditions and equipment types is essential for effectively preventing and mitigating CO2 corrosion. A holistic approach that includes proper materials, environmental control, inhibitors, design modifications, and regular maintenance will significantly enhance the lifespan and safety of equipment exposed to CO2 corrosion. CO2 corrosion inspection and monitoring based on API 571, Number A, VT, UT and RT inspection techniques should focus on general and local loss in thickness where water wetting is anticipated. Number B, preferential corrosion of weld seams may require angle probe UT or RT. Number C, corrosion may occur along the bottom surface of the pipe if there is a separate water phase, at the top surface of the pipe if condensation in wet gas systems is anticipated, and in the turbulent flow areas at elbow and tees. Number D, monitor water analyses, pH, Fe, etc., to determine changes in operating conditions. Detecting CO2 corrosion damage is crucial for the integrity and safety of equipment, especially in industries where CO2 is prevalent, such as oil and gas, chemical processing, and water treatment. Various inspection and monitoring methods can be employed to identify and assess CO2 corrosion. These methods can be categorized into visual inspections, non-destructive testing, or NDT, and continuous monitoring techniques. Number 1 is visual inspection. Basic visual examination. Regular visual inspections can reveal signs of corrosion, such as pitting, rust, or unusual surface textures. While basic, this method is essential for identifying immediate issues. Photographic documentation. Taking photographs during inspections can help in tracking corrosion progression over time and provide a visual reference for maintenance. Number 2 is non-destructive testing, or NDT. Ultrasonic testing, or UT. This method uses high-frequency sound waves to measure material thickness. It can detect localized corrosion, such as pitting, and provide an overview of wall thickness over large areas. Magnetic particle testing, or MPT, useful for detecting surface and near-surface defects. MPT involves applying magnetic fields to detect flaws in ferromagnetic materials. Eddy current testing. This technique uses electromagnetic induction to detect surface and near-surface corrosion. It is suitable for materials that do not respond to magnetic fields. Positive material identification, or PMI. This technique is used to verify the chemical composition of materials, ensuring that inappropriate materials are not used in corrosive environments. Radiographic testing, or RT, using X-rays or gamma rays. This method can reveal internal defects and thickness variations in materials, useful for assessing corrosion behind coatings. Number 3 is electrochemical techniques. Linear polarization resistance, or LPR. This technique measures the polarization resistance of a metal surface to determine corrosion rates. It's often used inline to provide real-time data. Electrochemical impedance spectroscopy, or EIS. This method involves analyzing the impedance of a system containing the metal and the corrosive environment to assess the corrosion behavior over time. Half-cell potential measurement. This is used primarily in reinforced concrete structures to assess the likelihood of corrosion of steel reinforcements, measuring the electrochemical potential. Number 4 is corrosion monitoring systems. Corrosion coupons. These are small pieces of metal placed in the environment being monitored, which corrode at a known rate and are periodically weighed to quantify corrosion rates. Smart monitoring systems. These may involve advanced sensor technologies that provide continuous data on corrosion rates, including automated corrosion monitoring sensors installed in critical locations. Number 5 is other monitoring techniques. Visual inspection robots or drones. Use of robotic systems or drones equipped with cameras can facilitate inspections in hard-to-reach areas, providing high-resolution imagery without the need for scaffolding or ladders. Thermography. This non-contact method uses infrared cameras to detect thermal anomalies that may indicate corrosion under insulation. Acoustic emission testing. This technique monitors stress waves produced by crack propagation or corrosion events, providing real-time data on the integrity of structures. In conclusion, choosing the appropriate inspection and monitoring method depends on the specific application, the materials involved, environmental conditions, and the required accuracy of detection. A combination of these methods often provides the most reliable assessment of CO2 corrosion damage, helping organizations to implement timely maintenance and mitigation strategies to ensure safety and performance. Regular inspection and monitoring are essential components of a comprehensive corrosion management program. Thank you.